Good evening, everyone. Today is the eighth session of our lecture series, and I would like to invite Civil Engineering Sectional Committee Chairman, Engineer Mangala Silva, to do the welcome. Over to you, sir.
Yes, Banduka, thank you very much. Dear participants, I'm Mangala Silva, Chairperson of Civil Engineering Sectional Committee for this session in IESL. Actually, on behalf of Institution of Engineers Sri Lanka, I would like to warmly welcome everyone for today's lecture. Actually, we all know that today topic. According to the topic that we published, it's about how to design the beams for direct shear. So, but I know with our old experience, we all know that. I mean, generally, when Professor Jasing is going to do a lecture, he's not only going to limit into that particular topic. He's giving so many additional details. I hope today also it will be the same. And also at this point, I would like to mention, and I'm really happy to appreciate Professor Jayasinghe's work for doing this particular lecture series free of charge. I'm getting so many good comments for this particular lecture series, and also during last 2 weeks, I received many comments saying that, I mean, there were so many students and so many engineers propose some new topics that Professor Jayasinghe can do the lectures, but we will concentrate on those things after doing this lecture series. So with that introduction, I would like to invite Professor Jayasinghe to do the lecture. Professor, over to you. Thank you.
Thank you, Mangala. Can you hear me?
Yes, sir.
Yes, sir. We can hear you.
Good. You good. Just give me 1 minute until I open the.
Okay, sir.
One moment. Until I open the files. Right. Right, so I'm going to, now you can see the white sheet.
Yes, sir.
And today we are going to start a new topic. And last time I talked briefly about torsional shear, but today we are not going to talk about torsion. We are going to talk about direct shear. Because once you learn about direct shear, it's so easy to learn the torsional shear. So, direct shear. First question, why do you get direct shear? We have a member, beam, subjected to two loads, W1, W2. We apply it here. Where are we resisting? At support A, B, C, and D. That's where we are resisting. So if you are applying a load here, resisting here, there should be shear. Call it shear. So whether it's a UDL, you have a UDL, we must have the bending moment diagram. Whenever there is bending, what is the next thing that happens? We will have shear. And the shear force diagram goes like this. And we approximately say the shear here cannot exceed 0.6 times F, where F is this F. F is equal to L times 1.35 GK plus 1.5. So the total load on a beam. So it's so easy. You don't do any calculation. Calculate the total load on a beam. If you have a building having a grid like this, and these are one-way slabs, where the load goes. This the load goes to this side, this is a plan way. So these are columns. Columns. So you know the load. And if it's an office building, we say it's 12 meters squared. And if this span is 4 meters, then 12 into 4. So this will be subjected to 48 kilonewtons per meter. 48 multiplied by these spans are 7.0 meters. So straight away we can see what's going on. So we'll have a beam subjected to a load of how much? 48 kilonewtons per meter. And what is the shear? Shear will be 0.6 times 48 multiplied by 7.1. Straight away we know the shear. So in British code, the approach was simple. So today is 24th January 2024, Civil Engineering Sectional Committee, lecture number 7 or 8?
8, sir.
Lecture 8, and this is page 1. This is clear. Why it's 0.6? It cannot exceed 0.6. So we know the maximum. We know the load, we know the maximum. But this here comes where? Comes at the support, where the support can be a 500 by 500 column. This 500 by 500. So in the British code, we are drawn like this. So what is the value, Bandhuka? What is the value? 0.6 multiplied by 48 multiplied by 7?
201.6.
202. We say 202. So we say this 202. Again, we go like this. Then there are two important sections. Let's say we are using 600 by 400 B. So there are two important sections. One is the face of the sun. Other one is D, simple D, away from the face of the support. So 545 millimeters away from the face of the support. So if I do an exaggerated diagram, larger diagram. So this is 250. This is 545. Because here the D is 545. You know the reason. The cover is 35 millimeters. So we have this. So this is the face of the support. This D away from the support. Face of the support. Why are they two so important? The reason is, if you take a section of a beam simply supported. This is a bending moment diagram. This is the shear force diagram. Shear force diagram. When the bending moment is 0, shear force is maximum. So if you take a element here, what do you get? Only the shear, complementary shear. Stress, sigma 0. So you can draw a Morse circle. 0, tau, minus tau, 0, tau. And you find the principal stresses are like this: tension, compression. So what is the failure type? It's shear. What is the fear failure? A crack like this, where the tension is pulling it. This tension is pulling it that way. So shear failure is a tensile failure. Shear failure is a tensile failure because this maximum stress that you get in the Morse circle will cause the shear failure, and it's a tensile failure. So it's tension. So how to prevent this? Links like this. So tension is taken by whom now? Tension is taken by the links. So we provide links. And shear failure can be prevented. So shear failure is a tensile failure, and tensile failure means we have to prevent it by using vertical reinforcement. Vertical reinforcement should be properly anchored. So what we say is vertical reinforcement should be in the form of links like this. Vertical reinforcement should be links, close links, or this shape. But we can have a closure. This is also possible. This is also possible. This is also possible. But this is called a torsional link. These are called shear links. What is not possible? This is not wrong. But the new link bending machines, they give you this. So you can buy this, but ask a man to bend like this and make it like that. And I generally keep this length as 10 times diameter of the link, because I would like to link it. So generally what you need is 6 times diameter. Generally I keep about 10 times diameter and bend. Is that clear? Bandhuga?
Yes, clear, sir. It's clear.
Very clear. Right. So that is shear. And we know the magnitude. And we can have two types of shear. One is you have a beam, no reinforcement, just these bars, no links. Then who will carry tension? Concrete has to carry tension. How do you rank concrete? Strong in tension or weak in tension? Very weak in tension. So all these capacities will depend on the double action provided by these reinforcements. So it's a function of 100 S over Bt. The double action, more reinforcement, bigger the shear strength. And then what else? Grade of concrete. Grade of concrete. And then the tensile strength. Generally, this value is between 0.4, 0.7 megapascal. So, bigger the section, this side, big section, small section, this side. Bigger the depth, close to 0.4. So for most of my calculations, I don't bother to check the value. I simply use it as point. Because the variation is so small to get any advantage, so I just use a value of 0.4, 0.45, not more than that. Most of the time you check the code and finally find 0.4 to 0.45 is the value that you get after calculation. So I just generally use 0.4. Right. So you have this situation, and that is, then you can see we have links, properly reinforced links. What happens? We can have this current compression, this current tension, this current tension. Who will provide the equilibrium? Current compression. Who will carry the compression? Compression will be like this. Carried by whom? Concrete. But concrete is a very strong material, but it is not super strong. So there is a maximum value stress in compression leading to failure of concrete. It's a maximum value. It's about 4.8 megapascal in BSA economy. Maximum is about 4.8 megapascal. Why? We use 20, 25, 30 megapascal cube strength. And the maximum stress that we can allow in compression induced by shear is only about 4. Because if you use about 5, 25 into something like 0.25 comes to about 6.25. So with all these additional factors of safety, we say, okay, we can allow a maximum value of 4.8. Because when you use 25 cube strength, the actual strength is 20, 20 multiplied by 0.25 is 5. So you can see generally the values vary between 4.8 to 5.3. So it's a very small variation. So generally I have a rule. Maximum shear capacity is 5 in fact. If the maximum shear capacity is 5, minimum is 0.4, what shall I do? I generally select the section. Shear, maximum shear at the support. So here is 202. Is that right, Bandhuga? 202.
Yes, sir. 202.
Now I have to draw a diagram. So this is 7,000. Center to center. Face of the support 6,000. So I have to say 3,250 multiplied by 3,500 multiplied by 200. What is the value, Bandhuga? 180. What is the value?
187.5.
188. Now what do I do? 188. Simple V is equal to 188 multiplied by 10 to the power 3 divided by width 400. Let's calculate by start with 600 by 400 section.
Yes,
600
600 by 400.
Okay. 600 by 400 section. What is the value? This is the shear stress, average shear stress.
0.862.
0.87. Okay. What is the maximum? Close to 5. Minimum is about 0.4. This is 0.87. How to provide links? Links are not provided here. We are going to check whether it can fail in crushing of concrete. So, stress is 0.87. What is the maximum? 5. Can it fail? By crushing of concrete? No, it cannot fail by crushing of concrete. Why? Maximum is around 5. But at the face of the support, maximum shear is 0.87. Can it ever fail? By crushing of concrete? Never. Now we come to the next phase. Now for this, I'll say the effective rate is 550. So here we have 250, another 550. So that gives 800. Then I'll say B is equal to 100, 202 multiplied by 2,700 or 3,500 minus 800 divided by 3,000. What is the value of Bandhuka?
155.82.
56. So
Yes.
simple V is equal to 156 into 10 to the power 3 divided by 400 divided by 540.
0.715.
7. Then we look at the BS formula. Says ASV OSV B V minus VC 0.87. Yeah. Very simple. Okay. Very simple. Now, what would I do? Now you can see here we have a term called V minus VC. Now if V is 0.45, VC is also 0.5, what do you get? 0. Then you get infinity. That is not good. You can't get infinity for the link spacing. Because this is 0, it goes there, you get SV as infinity. Can't be. So then it says V minus VC should be greater than 0.4. V minus VC should be greater than 0.4. So anything less, if V minus VC is less than 0.4, we say ASV OSV is equal to B 0.4 divided by 0.87. And we call this spacing SV is equal to ASV 0.87 FYV 0.4 times V. And in this equation, ASV means if you are using 8 millimeter bars, 50 here, 50 here. ASV means 100 millimeters square. Got it?
Yes, sir.
But ASV is known, SV is equal to 100.87 into 500 divided by 0.4 multiplied by breadth. Point. What is the answer?
271.87.
200?
271.8.
200.
271.8.
And if you are using 20 millimeter bars here, Eurocode allow you to use 20 times 20, 400 millimeters. But you can't go for 400. So you might select 275 or 250 for the next. I would select 250. Why? Because I would like to have little extra reinforcement to assure that overloading can be tolerated easily. Why? I like a failure in flexure. I don't like a failure in shear. What is the reason? If a beam fails in flexure, what can you do? You can bring a steel plate and fix the steel plate at the bottom of the beam. Now the beam will be okay after jacking the beam. On the other hand, after jacking the beam, you will use FRP treatment. Fiber reinforced polymers, carbon fibers. What will happen? Beam will be okay. But if there's a shear failure with diagonal cracks, very difficult to repair. So because of that reason, I don't mind being little generous with shear links close to the supports, not elsewhere. Got it, Bang?
Yes, that is clear, sir.
Right. Now, let's assume that this load is double. Now we got a load of 202. It was doubled, which means instead of what is the value? We got 156. Instead of 150, now you get 312. Now let's assume that beam has been overloaded by somebody and we are getting a load of 312. Now what is V? 312 into 10 to the power 3 divided by breadth 400 divided by depth 700, 545, and you got the answer will be 1.42. Is that right, Badhuga?
Yes, sir. 1.4.
Now we have to substitute. Why? In the first equation, ASV over SV is equal to V minus VC over 0.87 F5V. And now ASV is 100, SV breadth 400, V minus VC. So this is 1.42 minus 0.4 is a large beam. What is SV then? Bandhuka?
106.61.
So which means better to use 10 millimeter H10 bars, and for H10 the spacing will be a 61 into 50, 78.4. For H10 bars the spacing will be more. So how much you get? 150?
167.3.
So what are you going to do? We're going to do this. We are going to calculate simple V as 0.4. Capital V is equal to 0.4 multiplied by how much? 400 multiplied by 540. What is the value of V? So this is what the nominal reinforcement can carry. How much is it? 0.4 into 400 multiplied by 545 into 10 to the power minus 3.
Yeah.
How much?
87.2.
80?
7.2.
80. Now you can see I have doubled the nodes. So the center is 404. Goes down like this. And here at the face, I got 180 something. 180 face of the support, we got face of the support, we got 188. But it will be 366, 376. And then there will be another section where it's 87.2. So what are you going to provide? Here, H10 at 150. Here, H8 at 250. So you can decide where you are going to provide nominal links, where you are going to provide design links. So here, design. Here, nominal. Is that clear, Manduga?
Yes, clear, sir.
When the shear force is low, we can go for nominal links. When the shear force is high, we must design the links. So in BS 8110 method, we say we are using a truss analogy. Truss analogy. What is a truss? Beam is like a truss. So what is the purpose of this? Compression along with concrete. What is the purpose of this? Tension. Like a truss. But truss cannot be like this. You need diagonal members. So what are the diagonal members? Compression. Concrete. So in reinforced concrete, the diagonal members are out of concrete. Is that clear, Bandhu?
Yes, clear, sir.
And in BS 8110, this angle is 45 degrees. And that's the place where the Euro code is. Okay? So this is what the BS is. Now let's look at what the Euro code says. The equation for Euro code is given I'm going to share. So under 6, so it has a lot of things. And under 6, so this is all about the column design. And then we come to 6. Is all about columns. You can see, it doesn't, it's written, well written, but, doesn't look very friendly. So this is all about pre-stress concrete. Okay, now we come to the design. Under section 6, bending with or without axial force. The assumptions are plane sections remain plane. The strain in bonded reinforcement of bonded presence and whether in tension or compression is the same. Tensile strength of concrete is ignored. In concrete in compression are derived from stress strain relationship. The concrete strain in concrete shall be limited to ECU2 or C3 depending on the stress strain diagram. Talking about stressness. This is a stress strain curve for concrete. Can you see epsilon C2 and epsilon C3? The CU3, epsilon C2 and epsilon CU2. Those values are given in which code, which table? Here, you can see those values are given in this table. Is that clear, Vandukar?
Yeah, yes, sir. That is clear.
Yeah. So we'll look at code again. And then it says shear. Flexion is very simple, but it doesn't give equations. So for flexion, we have derived equations. That's what we did last time. When I said no need for equations, shortcut methods are available. Also available. Then this talks a big about VRDC, the design shear resistance of a member without shear reinforcement. That is based on 0.4, 0.45 value. VRDS is the design value of shear force which can be sustained by yielding shear reinforcement. That means VRDS is with shear reinforcement. VRD max is, can you remember I told you 4.8, 5 range? VRD max
Yes.
is 4.5 to 5 range. This, what you get with when you have reinforcement. And this inclined portion is for pre-stress concrete, so you don't have to worry. This CCD and VTD are pre-stress concrete terms, so you don't have to worry. Because we are dealing with RC design. So RC design, the shear member shear reinforcement is equal to VRD is equal to VRDS only. And if the regions VRDC, what is VRDC? That is the shear resistance of a member without shear reinforcement. Can you remember? I just calculated the nominal link area, calculating some
Yes.
87 force.
Yes.
So that refers to nominal link area. So VRDC is for nominal link. VRDC is for nominal links. And then it says when no shear reinforcement is needed, still you have to provide the minimum shear reinforcement. That is given in section 9. All the minimum values are given in section 9. In regions where VED, what is VED? The actual shear force. Actual shear force, the design shear force is more than the one that can carry without links, then you must provide shear links. It's same thing. And to calculate VRDC, it gives an equation. Gives an equation with a minimum value. And there are big equations, but what is the value you get finally? 0.4 times or 0.45 times the cross section. All these are big calculations, but what is the final answer? Around 0.4, around 0.45. But the important thing is if you have pre-stress, then you can get a higher value. So this equation, this is the pre-stress part, this is the RC part. So RC part comes first, pre-stress concrete part comes next. Is that clear, Madhuban?
Yes.
But
that is
whatever
clear.
you do, what is the answer? 0.4.
Around 0.4. Yeah.
Around 0.4. So you can do any calculation, but the answer is around 0.4. That's how you create rules. The moment you do that, your calculations become very, very, very simple. Why? You know there is a big equation given, but the answer is around 0.4. Then there are so many things. This is a pre-stress rule, so we ignore it. So then there are other parameters. And doing all the complicated things, finally it says, if you want reinforcement, the reinforcement requirement is given by VRDS with shear links, SW or S, that is SV, Z, F, Y, WD, cot, theta, where theta is 22 degrees. Good, theta is 22 degrees. Cot theta, can you see this equation? This equation. Cot 22 is equal to 1 over tan 22. What is the value of 1 over tan 22? 1 over tan 22?
2.47.
2.47. So generally it's called 2.5. So VRDS is equal to ASW. ASW. So shall we use the value that we got? What is the value that we used in the last example? We used VS 312. So let's say this 312. 10 to the power 3. ASW is 78.5 into 2. 150 SV. We don't know. We like to find it. Is it 0.9 times D? If you see Z in any equation, Z means lever arm. Lever arm is considered as 0.9 for shear calculation. Multiplied by divided by multiplied by 0.87 multiplied by 500 multiplied by 2.5. But then what is the SC value? These 157 multiplied by 0.9 multiplied by 545 multiplied by 0.87 multiplied by 500 multiplied by 2.5 divided by 3,312 into 10 to the power 3. What is SV?
268.41.
Can you remember British code gave a higher value? A lower value?
Yes.
British code gave 150, 167. This gives slightly higher. So Eurocode is more advanced in shear design. But in Eurocode also we have only one equation. And that equation is given in the code. Then you got to ask, what is this theta? What is this magic theta? How you get theta? That's where the complication. Otherwise, find the shear reinforcement. According to Eurocode, how many equations? One equation. Straight away you can find it. And that equation, not shear. Equation 6-8. One equation. Only one equation. Very easy. So many people say, oh, shear design is a nightmare. No, it's not a nightmare. Then, what is the speciality? What is this theta? That's where the complication comes. It says, when the concrete fails in crushing, at the face of the support, theta can be less than 22 degrees or theta can be between 22 and 45. What it says is, check and see whether theta is less than 22 or theta is between. How do you achieve that? How to do this check? For that we look at the code. This says VRD max is given by some equation, equation 6.9, and it's a big equation. Alpha CW, BW, Z, new one, FCD divided by cot theta plus tan theta. Big equation. The big equation. So, how are we going to deal with it? First, assume theta is 22. Substitute in this one, and alpha CD, alpha CW is equal to 1 for non-precedence concrete structure. Alpha CW is 1. Okay, good news. Alpha CW is 1. BW, we know 400. Is it 0.9D? New one? For new one, there's the equation. New one. What is new? New is 0.6 times 1 minus FCK divided by 250. New. Okay, we know new. The strength reduction factor for concrete fractal shear given by this equation, the equation I have shown. FCD is FCK divided by gamma m or FCK divided by 1.5. So now you can see the whole equation is here. The values are here. What shall we do? Substitute. VR max with angle as 22, 1.0 into 400 into 0.9D, 545 multiplied by new one. So that is, we are using 30 megapascal concrete. So this comes to about 0.53. This 30 divided by 250. So it comes to about 0.88 multiplied by 0.6, about 0.53. And 1 over tan 22 plus tan 22. 1 over tan 22 is about 2.5, 2.47. Tan 22 comes to about 0.4, I think. So what is ERD maximum, Mandukar? What is ERD max? Multiplied by 10 to the power minus
10 to minus 3.
Yeah.
Yeah.
So what is the value?
36.117.
Can't be 4. It has to be more. It has to be something like 400, 500. It's a big value. What is the value, Bandhu?
I'm getting the same values.
Huh?
Is it 1 into 400?
So 1.0 multiplied by 400 multiplied by 0.9 into 545.
Yes.
Multiplied by, so this should be 0.53. Is that right? I mean, around 0.53.
0.53, yes.
Yes. This is 1 minus, it's about 0.6 multiplied by 0.9. What is that? Tan 22 is 2.1 or tan value is this way. This whole value is 2.47
1 over tan 22 is 2.47.
plus tan 22.4. That is 2.87.
Sir, I think you
2.87
missed
is,
FCD.
yeah.
You missed FCD, sir.
FCD. Yeah, that's the
ZT.
reason. Oh, yes. Multiplied by 30 divided by 1.5. 30 divided by 1.5. Oh, multiply the whole thing by, FCK divided by 1.5. It's missing. Now, what is the answer?
700.
Multiply your ultimate 30 divided by 1.5. I'm sure you are getting 450 or something. Or 600.
722, I got.
Okay, good. That's the correct answer. Now, all do a simple calculation. 722 raised to the power 3 divided by 400 divided by 545. What is the answer? Close to 5.
3.31.
3.3. Okay. Can you remember the magic number? 5, 4.8 and 5. So what it says is, if the shear stress is 3.31, angle is 22. If it is close to 5, 3.31. If it is close to 5, what is the angle? 44. So how can I avoid all these extra calculations of finding the angle of shear failure? What I do is, I make sure the maximum shear is less than 2.5. So how can I control the maximum shear stress? Because I am the guy who selects the width of the beam. So if the shear stress is too high, I increase the width of the beam. And I keep the maximum shear less than 2.5. So do I worry about the angle then? Angle is always 22. Got the point? Now if the angle is more than 22, then that means if the shear is more than, it's around 900, 850 or 900, what will happen? Angle will be more than 22. Because I am moving, because it can vary between 3.31 and around 5. The shear stress maximum can vary between 3.31 and 5. So what shall I do? What I do is I will keep the shear stress, maximum shear stress less than 2.5. Then what will happen? I don't have to do any calculation because the angle is 22 anyway. Got the point, Bandhu?
Yes, sir.
Because if the shear is high, I have to find the angle. Why should I bother to find the angle? Because I am in control. I am the guy who selects the width of the beam. So I select a bigger width. And keep the shear stress down. Can you understand it?
Yes, sir.
So when I'm selecting the general arrangement drawing, how could I do that? Okay, I have a building heavily loaded. Say we said 1.35 GK plus 1.6 UK is around 20. A warehouse. And these beams are also, let's say, one way, 8 meters long. And so these are about 5 meters, 4 meters. These are 9 meter spans, 4 meters, heavily loaded. 20 into 4, 80. 80 into 9, 0.6 times 80 into 0.80 into 9, 9. What is the value? Big shear.
$432.
Still it's less than 720. Still it is less than 722. Will I have a problem? Less than 722. Will I have a problem? I don't have a problem. Why? Because you can see most of the 99% of the cases, what is the angle theta? Less than 22 degrees, so it is 22 degrees. Got it?
Yes.
Now I have showed a very long beam, 9 meters long, heavily loaded, 20 kilonewtons per meter square. So each beam will carry 80 kilonewtons per meter. Still, it's not possible to reach this around 3.3 value. Shear capacity is 720. So there's no way you can come there. So in Eurocode, don't worry. What is the way? Select a width so that shear stress at the face of the support is less than 2.5 megapascal. When you do that, theta is 20. Is that clear about this?
Yes, sir. Very
Because
small.
you are the person who select who draws the general architect or the engineer. Engineer draws. So engineer can do a simple calculation and make sure the shear stress remains less than 2.5. So you angle is 20. And you don't have to do any complicated calculation. In textbooks, shear is a big mess, huge calculations. But you don't have to do it. Why? Because we go around it and we make sure shear is the value that I want, not the code wants. Code has covered all the possible scenarios. That doesn't mean I have to calculate all the possible scenarios. I'm the design engineer. I decide what I'm going to do. So I decide I'm going to select a width large enough so that the maximum shear stress at the face of the support will be less than 2.5. Definitely the angle will be 22. Got the method? Panduku?
Yes, sir. Yeah.
You can understand, huh?
Yes, sir.
How about the others? We have over 90. So how about the others? So if you look at Mosley and Manji, any book, even the design example I have given, because I have to cover all the possible scenarios. So the design example, even in the design example, I have covered it in great detail, considering all different scenarios. And so you can see a lot of big equations. But don't worry. So I have given a complete example, and with the flexural part of the example, then this is a shear part of the example, and so at each support, the calculations are given. Then these equations are given. The minimum ratio equation is given. Yeah, in under section 9. Big calculations. But then I'll also look at the simplified. Just one moment.
Okay, sir.
Till I get the note. Let's see. Yes. Okay, so I will show you how we deal with it. I'll share the screen. If you look at this note,
Yes, sir, we
where
can see.
you have this note. I think you have shared it, Bandhuka. To
This
simplify.
one.
Notes. See here. So all those values are available as tables. So you don't have to actually calculate. Ultimate shear stress of, so I told you it varies between 0.4, 0.4 range. But
We have shared these notes.
yeah, these values are there. So likewise, you know, the simplified formula available. So you know, what is the difference between Euro and BS? BS code gives this table in the code. Euro code gives one equation. It says if you want, you can. So that's why, you know, the advantage is, you know, you can make use of these simplified tools. So Vanduka, I mean, any questions on this?
There was one question.
Yeah,
That
what
is,
is it?
can we enhance the shear capacity if we can provide proper anchorage to longitudinal reinforcements?
No, actually that's something different. It comes slightly different way. I'll share the screen, I'll show you. Here you can see something. The additional tensile force, delta FTD, in the longitudinal reinforcement due to shear, VED, may be calculated from this. Again, for theta is 25 degrees. So 22 degree. And it's given as 0.5 VED for theta. What does it mean? That means you must provide some longitudinal reinforcement to provide the equilibrium. So don't get a lot of reinforcement in when you are doing the shear design according to Eurocode. You have to be little careful when you are curtailing the reinforcement. So generally, when you are curtailing, you will make sure that in the early days we used to have the hanger bars as the smaller reinforcement, and additional reinforcement used to come in the middle. But that is not the practice that we do now. Now we run the larger bars as hanger bars, and then we provide smaller bars as additional. Why? If you have the smaller bars as hanger bars, you can't satisfy this condition. So to satisfy this condition, you have to put the larger bars as hanger bars, the outer bars, the inner bars can be disconnected. Have you got the point, Banduka?
Yes, sir. Very clear.
Right. So you have to be very careful in design, shear design. When you are curtailing, especially in Eurocode, the curtailing methods are very different. So you have to curtail the smaller bars, not the big bars. Big bars must be running, otherwise you can't provide this shear capacity. Equilibrium. Equilibrium cannot be provided easily. Got it?
Yes.
And then when you go to section 9, it says the minimum reinforcement. Section 9. Section 9 is all about minimum reinforcement. Here you get it. Here you get it. The reinforcement ratio for shear is given by this alpha is 90. Sin alpha is 1. And then say the minimum ratio is given by this one. So there's a minimum longitudinal reinforcement. Sorry, the minimum shear length. There's a minimum. It's a minimum. Okay. Right. Just give me 1 minute. I have to open the door and come.
Okay, sir.
So Panduka, now I have given a design example. So design example is very complicated. If you are interested, you can have a look. But this is the crux of the matter. So, but if you are for completion, I have given one example in the note, and you can see all the calculations very clearly given in the example. But there's a small mistake in the example. In this formula, there should be a value of D. D is missing. The depth should be 600, 545. You have to multiply it by 545, but here I have not multiplied it, so there's a small mistake here. Other than that, this note is perfect. There's a small mistake there. So if you go through this example, you can learn a lot. Go through this example, you can learn a lot. Take your time, go through it, but be aware that there's a small mistake here because I have forgotten to multiply it by D. The equation has D, the effective depth, but I have forgotten to multiply it by D. So just be aware of that. Other than that, it's perfectly done. All the examples, everything is there. But the method that I have taught you is far easier than the method given here. The reason is, the code, the code basic books like Musli and Bandi, they are trying to cover everything. But I have shown you how to avoid all the trouble. What is the trick? When you are selecting the width of the beam, we'll make sure the maximum shear stress is around 2.5 or less. Then angle is 22. Whatever we like, whatever we try to do, angle will be 20. But if the shear is high, the angle can vary between 22 to 40. That is the unlikely case because when you are designing, I don't like shear to govern. Why? Shear failure does not give enough warning. How about fractional failure? It gives it warning. So I like beams to fail in fraction, not in shear. So I make sure shear capacity is excessive. Flexural capacity is sufficient. How could I make the shear capacity excessive? I use a wider beam. not a very narrow beam. Very narrow beam shear capacities are low, wider beam shear capacities are high. If the beam is heavily loaded, I will use a wider beam. If the beam is very lightly loaded, then the shear is not critical anyway. Have you got the point, Bandhuga?
Yes, sir, that is clear.
So there's a very well done example in the notes, so please go through it. And if you want more information, go through the examples given in Musti and Banji. And then there's another set of notes, foundation note. They also I have done. I have this note on foundations. In the inverted T-type foundation design, you can find all these calculations again. So there are so many design examples around. You can make use of it. Anyway, when I cover the foundation designs, I will show you how to use it. The same equations will be used over and over and over again. But you can see for flexure, I have given a simplified method, or you can use the equations. For shear, I have again given a very simplified method so that you can use one equation, forgetting about all the complications that are being created by you. And still our designs will be optimum because I don't like shear governed designs. I like always flexure governed designs. So Bandhuka,
So there's a question.
yeah,
How we can apply retrofitting methods to shear failures?
that's a good question. So I mean, if a beam has failed in shear, you better check why it failed in shear, because generally shear failures don't happen, right? Now, if you have seen a shear failure in the structure, be very careful because something really wrong with the design engineer. That's how I put it. Because if the design engineer has been vigilant, there cannot be shear failures in structures. And retrofitting, what is the method? Very simple. You have a column, you have the shear failure. You fix a steel bracket here using pre-stressing type bore rods. Fix it, support it here. Now where the shear failure occurs, be away. By the time that you come to that place, the shear capacity, shear stress will be much lower. Could you understand the method, Bandhu?
Yes, sir. That is clear.
Very simple, because always shear failure occurs, be away from the surface of the support. So you remove, you change the face of the support by having a steel bracket. Got it?
Got it, sir.
Yes, sir. Okay.
And yes, and one
Be
more
careful,
question.
because shear failure is design engineer would be a nutty case. Because if the design engineer is a good design engineer, he will never allow a shear failure to happen. He will always make sure shear width is sufficient and shear failures never happen. The links are all there, so those are cheap. But he will make sure if the beam ever fails, it will fail in the middle due to flexural overstress.
Okay, sir.
Okay.
Okay, sir. And one last question, sir.
Yeah.
One member has put one sketch into the chat box. If you can see it, sir, is asking about shear link shape, which is in Indian standards.
Yeah. This is wrong. This is wrong. You have to have a hook. This is wrong. This is the correct one. No? You put this one, put a bar there, then use a cross. So this is a standard link. Where these bars are properly, and you don't have to cross everyone. After about 3 or 4, you can cross. What is drawn is a wrong diagram. You can't have shear links like that.
Okay, sir. And, that's also in questions in the chat box.
Yeah.
If you have,
So shall we write it?
okay, sir. Okay. And
So
I would
shear
like,
is very simple, but
yes, sir.
on the code it's very, very complicated. So don't
Yes.
fall into that trap. Never think that shear is difficult. Shear is easy. But you have to avoid all the unnecessary calculations that are given, which are not, I don't encourage people to design shear governed designs. It should always be flexure governed designs. So with shear we will be generous. And we can easily be generous. Even locally we can make the beam wider. Right?
Okay.
So don't go for shear governed designs, always go for flexure governed designs. Okay?
Okay, sir. And how about our next session? It is a continuation of our,
Yes, the next day, now shear is covered, bending and shear. And then we'll need to look at columns, and also we need to look at what are the things. Shear is there, torsional shear. Then shall we cover this torsional shear also in the same time?
okay, okay, sir.
Then it's good, because then shear is completely over. So next time we'll talk about torsional shear. Okay?
Okay, sir. Okay, sir.
Right, okay.
Thank you very much, sir. And I would like to invite Engineer Nalaka Senavidapna to do the vote of thanks.
Thank you, Engineer Banduka, for giving me this opportunity. First of all, I would like to thank Professor Tisan Jayasinghe for conducting this lecture series to uplift the knowledge of civil engineers as well as civil engineering students. Thank you once again, sir, for your knowledge sharing. And also, I would like to thank the chairman of Civil Engineering Sectional Committee, Engineer Mangala Silva, for initiating this kind of lecture series. Thank you very much, sir. Also, I'd like to thank ISL Secretariat, IT Department, and the Publicity Department for hosting facilities for this lecture series. Finally, for all the participants, your internets and active participations make this lecture series success. Thank you all.
Thank you, sir. Thank you. Good night.
Thank you, Bandhu.
Thank you very much.
Thank you. Then I'll leave.